My name is Deepyaman. As mentioned, I'm a software engineer at Voltron and at Voltron Data. And today I'm excited to share some of the work we've done and subsequently open sourced on unifying a stream and batch processing with Ibis. So as mentioned, I actually joined Voltron Data when they acquired Claypot AI. So much of the streaming foundations in Ibis were actually built when we ourselves were Ibis users, leveraging it to build the API for our real-time machine learning platform. So what is Ibis? We'll dive much deeper into that in a moment, but it's an open source, portable data frame library maintained and contributed by a lot of wonderful people. You can see a lot of them there. You've probably seen at least one of them at the conference. Also, as I learned after the fact from a friend, they are also a nuisance bird in Australia. They're considered bin chickens because of their proclivity from eating garbage. But we're going to focus more on the portable data frame library definition today. Anecdotally, I have seen an uptick in the community talking about Ibis recently, very exciting. I'd usually start off by asking you all who's heard about Ibis, but I know like half the people in this conference were at Wes's talk, so I'm just not going to do that. So, start motivating Ibis. Have you ever found yourself in a position where you're translating data engineering code from pandas to PySpark? Have you been prototyping something in pandas, then thrown that over the wall to a data engineer? Probably a lot of people, you might have been that data engineer. Also, have you ever used Parquet as a cross-language serialization format? I've previously asked this in a smaller audience, and almost everyone raised their hands. But why is this the case? That's because when we look at the Python data stack, the PyData stack, a lot of the tools that you see over there on the screen, they're basically predicated on a couple of assumptions. One, data is going to be local, and second, it fits in memory. So what does your workflow look like? Let's say that you're working with pandas. If you're not familiar with it, that's this logo over here on my right. You've got data in Postgres, so that's represented by that elephant. So what you can do is essentially you can connect once, decide on what data you want to access, and you can slurp up that entire table. Then you can do your whatever loading data, parsing, whatever computation you want to do on that data, you can basically work with it. And this is your standard PyData development experience. Now, we have a problem. What you use locally, so that's going to be your pandas, maybe it's polders now, that's usually not going to be what you're just deploying to in production. Usually, especially if you're working with data of any reasonable scale, you're going to be using a distributed computation engine, whether it's going to be a separate framework like Apache Spark, or it's going to be like a distributed database, something like BigQuery or Snowflake. So we need to talk about SQL, and it is everywhere. It's been around for a long time, whether you're using like a traditional database or you're using one of those like OLAP databases, like your Snowflake, BigQuery, you're most likely going to use SQL. Already with things like SQLite, and now everyone seems to be using DuckDB, it's quite likely you're going to be using SQL in some capacity for local execution as well. And let's not forget about engines like Apache Spark. Yes, you have that Python interface, but and programmatic APIs, but Java API, Scala API as well. But using the SQL interface is also a very common way of using Spark SQL. So for SQL, there are a lot of good things. One is that it's standardized, more or less. There's more on that later. Second, it's concise. At the same time, SQL has its share of drawbacks. First off, it's effectively untestable. I think the last talk, actually, Alkan talked quite a bit about that. It's also, at the cost of being concise, it's sometimes inscrutable, and it can fail at runtime. Also, I just happened to learn this morning from somebody that apparently AI is also not as good as writing your SQL, so maybe that's another drawback. That said, there's still going to be a lot of people who say, just use SQL. So let's try that out. Let's see what that experience looks like. So the first step I'm going to do is I'm going to conjure up a SQL query locally in whatever environment I'm developing in. There's not really a good local development story around this. Basically, you just need to figure out what you want to write, and you come up with that query. Then we get the feedback when we actually connect to that database, send over the SQL query. It gets executed on that remote database, and we get our results back. But there are some potential issues with this. First off, do we even have access to execute against a remote database, especially develop against production? Quite possibly not. In many organizations, I'm sure, production is essentially locked down. Dev instances exist, but they're not necessarily known for having pristine data. So we did say that we can run SQL everywhere including locally. So maybe that can help us out with our local experimentation aspect instead. Instead of just conjuring up a local query, what we can do is we can get some data in a local database, and then instead of magically coming up with a query, we can experiment locally, come up with that, and then when we're ready, we can go ahead and connect to that database, send it over, same thing, execute, and get back the results. Maybe that's a little bit better. Actually, maybe our problem is solved. It's not. So a few things, a few problems. So first off is the translation problem. We did say that SQL is a standard, but how standardized is it really? Can we simply take something that ran on one engine and expect it to work on another? So let's take a very simple example. Oh, this did not format well. So we've got data in 3 columns, and for whatever reason, it was ingested all as strings. So if we look at over on this side, you can see like the 1919 string or something, and we can get them to, and what we could do is what we could say is like, all right, I don't know why you ingested all strings, let's get upstream to fix it. Face it, I mean, realistically, that's not going to happen, so we're going to actually do this ourselves. So we're going to just clean it up, pretty simple operation. We're going to essentially cast it to number, and that should be simple enough. So let's see what this actually looks like. So we can already see it, just a simple cast operation. Locally, let's say we were using SQLite, and below, in this hypothetical example for remote execution, we're using Postgres. The only differences are we're casting in one case to in SQLite to real 53 and integer. The types in Postgres are going to be double precision and big int. It's a very minimal example, but we can already see that the dialects start to diverge. Moving on to another problem. The second one is the parameterization problem. So maybe we want to replicate some logic across like several regions of interest, or we want to have our query to have slightly different behavior based on the user and their characteristics. So should this be basically one massive query, or should it be broken down into a lot of smaller queries? If it is that, like, how do we even go about generating all of these queries? Would it be with like templating? Would we go back to our old friend Jinja? And then when we resolve those queries, how do we know that's actually going to work? What if for a certain user, we substitute null in places in the query, and then that ends up becoming invalid? So we've got a number of problems. We talked about translation problem, parameterization problem. Beyond that, I personally like Python. I don't know about a lot of you all specifically, but let's say there are a lot of people who are working in the ML and data space who really do like to use Python. And last but not least, maybe regardless of what you like, you might not want to write SQL. There's a fun quote on Twitter. SQL is really difficult at first, but once you use it regularly and learn more about it, it's even worse. And do we really want to even start talking about common table expressions, recursive common table expressions? So I know what a lot of you are probably thinking in the audience, and everybody at some point in their life, I'm just going to generate strings. And yeah, I'm going to tell you, or I'll let Drake tell you, just don't do it. In short, generating strings starts out simply enough, but it quickly explodes in complexity. And that's before mentioning that you don't have an out-of-the-box safety mechanism for that whatever queries you're generating are actually going to work. If you've still got your heart set on the solution, or if you just want to better understand some of the challenges associated with rolling your own string generation utility, I'd suggest taking a look at either Gil or Philip's talks previously. This is also probably a good time to mention that a lot of this background material on what is Ibis is credit to them, who are both maintainers of the core Ibis library at Voltron Data. Okay, so what do we actually do? What if, instead of generating strings, you could write concise Python code that gets type checked and eventually generates strings? And what if I told you that there's a library out there that does that for you? And that is Ibis. So Ibis is a lightweight Python data frame API. It provides the interface to 20 plus backends. And on top of that, it provides a deferred execution model. What does that look like? So going back to our similar sort of scenario, same as before. We connect to the database. But now instead of slurping up some data, we're actually just going to get back the schema information, the metadata for that table. And then we can develop, not on the data, but actually on the schema, we can build, compile, and generate a valid SQL query, which we can then send over, execute, get back the results for. One of the great things about separating query execution from expression generation is that we can actually get that schema from somewhere else if we want. So that could be like a metadata store, schema registry. Furthermore, another option is that if we already know what the data should look like, we can even define that schema in code locally. All right. So I know what you're thinking. This sounds like an amazing library. I'm going to just go download and try this right now. Great. Also, you're probably wondering, okay, I thought we were going to talk about streaming at some point, right? So Redux time. Have you ever had these problems? Like, have you ever been translating data analysis from pandas to something like Flink or PyFlink? Same as before. Have you prototyped it and then you've had to translate that? Then you've had to pass it over to a data engineer to do the translation. A little bit different. Have you ever duplicated the same logic in batch and streaming contexts? So to give that some context for this, let's say that you have some features that you compute on a daily or hourly basis right now, but you need them freshly available for a real-time model. For a lot of, actually previously, while working at Claypot AI, a lot of people already have all those queries and they want to move it over. And that means basically rewriting your logic in some other API like PyFlink. And last but not least, have you ever backfilled a streaming feature on a backing table? So without the fancy words, what we basically mean is, have you had a real-time feature that you then need to go back and compute on historical data? Let's say that you want to do training data generation. You can't just say like, okay, I'm going to generate training data for now, whatever data is coming forwards. When all of your other training data is on some historical subset, you need to go back and be able to backfill that. So I think, especially given this an audience of the streaming track, I'm sure a lot of you have probably also faced some of these challenges. So let me jump into this. Well, streaming is different. It's a bit of a different beast from batch, and thus far, Ibis only supported batch backends. You've got a lot of different sources and sinks in the streaming data world. Things like Kafka and a number of Kafka alternatives are going to be very core to that. There's also a lot of concepts that don't exist in a batch world. So for example, for real-time data, you have considerations around when the data arrives, so out of orderness, late arriving data, et cetera. To combat this, you have things like concepts like watermarks that you need to support. There's also the whole notion of event time versus processing time, and which one you should use in each situation. Something that's also not explicitly listed here, but some operations just don't make sense in a streaming context. For example, if you're going to do some sort of ordering over a non-time column, that's often not going to be, like a global ordering is not going to be supported in a streaming context. It just doesn't make sense to, let's say, sort by your order ID when you're not going to stop seeing new order IDs. Another thing is that table valued functions so these are things which are supported in a lot of other databases as well, but they're very core to real-time use cases. You're going to do a lot of things which are like windowed aggregations that you're going to want to compute over various windows of time. And so you need to be able to handle like various hopping windows, tumbling windows, things like that. And last but not least are temporal joins or as-of joins. These are also supported on some other backends. Like you can even support as-of joins and pandas, but they're very core to your streaming use cases because when you're working in a streaming context, like for example, your timestamps are not going to just line up that you can just do an equijoin or something like that on them. So yeah, you definitely need support for some of these things. All right, I'm gonna jump into a demo actually. Enough of this theory. Let me swap over. Okay. So this is the pre-recorded. Okay, I don't know if there's sound for this, so maybe I'll just voice over it. So yeah, for this example, we're going to just assume that we've got some mock payments data. We can take a look at what that data might look like up here. To begin with, let's just go ahead and pull some examples of this data from the topic. This topic is named payment message, unsurprisingly. And we can see like this looks about right. So we've got our various fields, order ID, pay amount, and pay platform, so on. So let's start with how we're going to do our local experimentation, how we're going to come up with this feature that we want to build. In order to do this, let's pull some number of rows, like 100 rows, so that we can do some local experimentation on top of that. So also, what might be a good feature to build here? We can potentially look at computing the average payment amount over certain 10 seconds. I think it was here. I have to remember. But yeah, so we've got some we've got some data here for local experimentation. We can use, in this case, let's go with the DuckDB backend. It's a great option for local development. It's actually what we default to in Ibis. Here, I'm going to go ahead and connect explicitly, specify ibis.duckdb.connect explicitly. But actually, if you did, I think ibis.connect also, like everything defaults to DuckDB. We could have also used something, I think, past iterations, maybe I would use the pandas pandas backend, but DuckDB is great here. We can see that our table is basically a representation of what that schema looks like here. And we can start developing our logic. It's a pretty familiar looking data frame API. yeah, so I was right. It was the, so we'll do the sum over the province ID for the last 10 seconds as our feature. You can see what that representation kind of looks like in terms of that internal like IR. Actually, yeah, I think we can go ahead and look at what that data looks like by turning on interactive mode. Let's see. Yeah, so if we go back up and look at that, we should be able to see what the data for AGD is. Okay, so I mean, this looks reasonable. I think because of the sorting, they're all ones here, but we could verify that these are not. If we look at the full data, we'll see it's okay. It's not just suddenly every province ID is one. It just so happens with that data that's there. Okay, yeah, I think we can. Yeah, so we can add in the create time. That way we can see that, okay, each of these ones with the same province ID is actually associated with a different create time. And this makes sense because we're getting, basically every time we get a new data point coming in, we're going to compute that, kind of recompute that feature value. It doesn't really matter from to have that create time when we're actually doing things in that streaming context, because like when we're inserting into something like a feature store, we're going to just basically use whatever's the latest value and replace that so that we can always pull the latest from serving perspective. But it's a good thing just to verify that's not giving us the wrong results. Yeah, and then I also, maybe I don't like the fact that the province IDs are all numeric. I'd rather map it to the actual, like, what is the province? And so I can just create a pandas table, for example, and that will create like an in-memory table for us that like Ibis is a concept of mem table, and I can join that, and you can see that getting populated here. In order to verify again that it's not just always giving the same result, we can use some of our standard like data frame like operations like a value counts, and we can see, okay, yeah, it's just because of how on this backend it's getting sorted in the data, but yeah, that's only 10 of the records. The remaining are all different provinces. Okay, so now let's get to the part where we want to actually be able to deploy this into a streaming context. There's still things that, from a backend specific perspective, we'll need to do. So, for example, for running on the Flink backend, we will need to go ahead and get that Kafka connector for Flink. We can just go ahead and download that pretty easily. There we go. And then for Ibis, so for example, when you connect to the Flink backend, you're just going to basically provide your connection information is essentially like your PyFlink table environment. This is similarly done for other backends, or for a database backend, you provide connection string. Spark, you provide like a Spark, like a similar like Spark session. But that just depends on a per backend basis. I'm going to also define what that schema is associated with the source, same as above. And then I should be able to connect. Let me go ahead and turn off the interactive mode here. And yeah, then we can connect. In cases where we need to do something special, like drop down into the backend specific code, so in this case, the add jar sort of thing, we can use the raw SQL method. Let me also go ahead and configure what that like source and what that source is going to look like, and then I can create a table using Ibis like standard API. For that, we do see one of those like streaming concepts like the watermark. So that's really only going to reflect itself not in any of the logic, but in the like source configuration in this case. After this, we can also just go ahead and configure our sink very similarly. And so for the sink, since we're doing the average amount by province, we're not going to sync the actual create time or anything in this case. So yeah, it's just going to be that province column with the string, pay amount with the float, and yeah, I can go ahead and create that as well. This is going to be a Kafka sink. Yeah, I just provide that information, and that should be created. Okay. Once I do that, the logic for the will be exactly the same as we had above when we did it locally on DuckDB. This is absolutely unchanged. Went ahead and removed that create time column again, but other than that, it's exactly copy pasted from above. And then we can go ahead and run that. You can see the whole kind of execution plan for this because we're not running this in interactive mode. We can also see, can be interesting, and also maybe like a sanity check to verify like what does that SQL compiled under the hood look like by Ibis. So we can see this all kind of makes sense. That mem table kind of gets in right now for Flink exploded into like a values table. And then we can go ahead and insert that into our Kafka sink. Last but not least, let's just go ahead and verify that, yeah, we're actually seeing those data in the resulting sink, and that all looks good. We've got our two columns, and it seems reasonable enough. So yeah, that's how we could basically take what we prototyped locally with DuckDB, move it over to run on a Flink backend with no code changes to the actual like execution logic, just minor configuration changes. One of the other things, which is kind of cool to look at, is we can actually visualize above what we showed that IR for the expression to be. So this is going to give us a graph-based representation of that. So we can see this is like how Ibis is actually building up that abstract syntax tree. It's a bit large to fit here, but if we scroll up, then we should be able to see all of that representation. Basically, all of these are what get compiled into through various rules to the SQL resulting SQL code that gets executed. We've seen a lot of stuff in the last 20-25 minutes. We got a crash course on Ibis, what it does, how it can help bridge the gap between dev and prod. Then we saw how we can extend that analogy to unifying streaming and batch. Ibis itself, as we mentioned, supports a number of backends out of the box. You can see a lot of them here. We also always welcome new backend contributions. For example, you can see Rising Wave here. That was actually our second streaming backend. That was something that none of the Ibis team, kind of helped with, but it was actually pretty much fully developed by the Rising Wave team, which was very cool. And we got that soon after the Flink backend. We also saw, for example, a little bit of the DuckDB backend in action today. So while we say that this can mean, for example, less rewriting between dev and prod, there are some caveats. Floating point math exists. So floating point math is not associative. So if you have a big chain of arithmetic operations, just be aware that you're doing that and check your answer. Also, it seems obvious, but only SQL backends can execute SQL. There are actually certain functionalities, like the .SQL function, that are only going to work on certain backends. But I'll note that you don't necessarily need to actually rewrite your SQL string that you're passing to that .SQL method if you're going to switch backends. So that function actually takes into account, you can pass a dialect for that SQL that you're passing in, and then each of the backends has an associated dialect, and it leverages SQL glot under the hood for that transpilation. I know that there are a lot of people from Tobiko Data here, so they can tell you all about SQL. It's very helpful for Ibis. Actually, in the latest release of Ibis, there was a major refactor to almost all the SQL-based backends are just leveraging SQL Glot under the hood. Finally, some backends are just too large. Some backend differences are just too large or intractable to abstract. So for example, every SQL engine seems to have its own flavor of how it supports regex, and Ibis hasn't found some magical way to unify these, at least not yet. Similarly, Ibis lets you maintain the same logic between streaming and batch as we've seen. There's some caveats again. They're still different, as we talked about a little bit. It's possible to view batch as a special case of streaming, so that's the Flink way. But as we discussed previously, some of these batch operators won't really make sense in a streaming context. There are also some open opportunities to make the gap smaller. So for one, there are places where we can automatically switch between streaming and batch execution and use the one which is appropriate for the situation. I think this is something that Flink is actually working on in its own vision to unify the two. Okay, so what's next? So one of the things is support for time travel queries. That's currently something that we're working on. This applies to some streaming backends like Flink, also to a number of batch backends, things like BigQuery, I think Snowflake. They all support some level of time travel queries. Across the board, we're also working on support for reading and writing to Iceberg and making sure that we're doing that efficiently, especially because that's something that's very commonly used together with Flink. And leveraging, so we want to make sure that we're leveraging the like predicate pushdown and things which are exposed by Iceberg. There's also experimental support for Delta and Ibis, and I mean, I didn't know about Xtable when I submitted this talk, but maybe we'll have that soon too. Pattern recognition is another thing which is kind of on our backlog to look at, and kind of again abstracting that over backends, though that does sometimes have a little bit more diverse syntax across backends. And finally, we're always adding additional backends, including additional streaming backends. I think the Spark streaming is definitely one that we're looking at coming soon, but yeah, I think work on that hasn't exactly begun yet. So that pretty much brings me to the end of my presentation. So I'll leave you with this. So please give Ibis a try if you haven't already. There are a lot of great resources up here. I realized maybe people don't know what this logo is. That's our Zulip chat. So feel free to join on that if you want to talk to the team, and or if you have just general support questions, as well as, of course, through GitHub. It's very simple to install. You can use just use pip. You can use Conda, Pixie, Mamba, whatever. I will note that pip install Ibis framework and with the extra backend works for everything except for Apache Flink, which is kind of bound on its PyArrow requirements. So you actually have to go and do a pip install Ibis framework and Apache Flink separately, so it doesn't downgrade PyArrow for everything else.